Hey there, and welcome. We usually think of math as just, well, numbers and equations. But really, at its core, it's a language. It's a way to describe all the amazing patterns and connections we see in the world. And today, we're going to learn the absolute fundamental grammar of that language, the mathematical relation. So, let's get into it.
So, to kick things off, just take a look at these 4 points on the screen. At first glance, they probably look pretty random, right? Just a bunch of coordinates. But what if I told you they actually share a very specific relationship? How would you even begin to describe that connection using math? Well, that's exactly what we're here to figure out.
To answer that question, we have to start with the most basic word in this whole language of connection, and that word is relation.
And here it is. It sounds complicated, but it's not. In math, a relation is just a set of ordered pairs. Seriously, that's it. If you have a pair like x, y sitting inside your set, you can officially say that x is related to y. It's just a formal way of saying, hey, these two things are connected.
So, the most important thing to get your head around is this. The ordered pair, that little x, y, is like the atom of every mathematical relationship. It's the smallest possible piece of a connection linking a first thing, x, to a second thing, y. A relation? Well, that's just a collection of these little atoms.
Okay, so every language needs some rules, some grammar, to actually make sense. And for relations, that grammar is all about two key ideas, the domain and the range. This is how we keep all of our x's and y's organized.
Let's look at a super simple relation, shown here in a table. You've got your inputs on the left, your outputs on the right. So what's going on here? We can see that the input -7 is connected to the output -9. And look at this, the input 2 is also connected to -9, and then the input 3 is connected over to 9.
So that brings us to the domain. That's the official fancy name for the set of all possible inputs, all the first numbers, the x values. For that table we just saw, the domain is simply the set containing -7, 2, and 3. It's the complete list of all our possible starting points.
And on the flip side, you have the range. This is the set of all the possible outputs, or the second elements. Now remember how both -7 and 2 pointed to the same number, -9? Well, in the range, we only list -9 one time. This is a key rule. The range is the set of unique destinations. So for our example, it's just -9, 9.
You know, just like any spoken language can have different dialects or accents, this language of relations can also be expressed in a few different ways. So let's check out these dialects of math.
There are 4 really common ways you can show the exact same relationship. You can list it out as a set of ordered pairs, kind of like a phone's contact list linking a name to a number. You could draw it as a mapping diagram, with arrows literally pointing from the inputs to the outputs. You can plot the points on a graph to see the visual pattern, or you can use a powerful equation to define it, and just a little heads up, when every single input has exactly one output, that's a really special kind of relation that we call a function. Super useful stuff.
So let's talk about graphing. And let's use that set of mystery points from the very beginning. The process is actually really straightforward. For each pair, you just find your x on that horizontal line, then you move up or down to find your y on the vertical line. And bam, you put a dot right there. It's as simple as that.
Now, just listing points is fine if you only have a few. But what if a relationship has an infinite number of connections? That's where equations become incredibly powerful. An equation, like x equals y squared, isn't just describing a handful of points. It's describing a smooth, continuous curve that's made up of countless ordered pairs that all follow that one simple rule. So, to talk about these huge, infinite sets that we get from graphs and equations, we're going to need some more advanced vocabulary. We need a kind of shorthand to describe a whole range of numbers without having to write every single one out, which would be, well, literally impossible. And here are our 2 main tools for that job. On the left, you've got set builder notation. It uses a rule to describe all the numbers in the set. On the right, you have interval notation, which is the super compact, quick and dirty version. See those square brackets? That means we include the endpoints, so we're talking about -8, 8, and every single number in between. 2 different dialects, but they mean the exact same thing. All right, let's put this new vocabulary into practice with a real example. Just picture a circle on a graph. The farthest left it goes is x equals -8, and the farthest right it goes is x equals 8. Its lowest point is at y equals -5, and its highest point is at y equals 5. So, how do we use our new tools to describe its domain and range?
Here's how it breaks down.
For the domain, the x values, we can write it in set builder notation, or that clean interval notation, -8, 8. Same thing for the range, the y values. We can write it out the long way, or just say -5, 5. See how much cleaner that is?
Okay, you have learned the basic words, you've learned the grammar, and you've learned the different dialects. Now it's time to really test your fluency. We're going to try and read the full story of a much more complex graph.
Take a really close look at this one. I want you to notice everything. We've got a solid dot where it starts, a nice curve, an arrow telling us it goes on forever, and, a curious little open circle. So the big question is, what is the complete domain and range of this entire relation?
Let's start with the domain, all the possible x values. The graph kicks off right at x equals 0. And since that dot is filled in, it means we include 0, which is why we use that square bracket. The arrow points to the right forever and ever, which we represent with positive infinity plus positive infinity. And here's the thing, you can never actually get to infinity, so we always close it with a parenthesis.
Okay, now for the range, the y values. This is the real tricky part here. You have to notice that open circle down at y equals -2. That's so important. It means the graph gets super infinitely close to -2, but it never actually touches it. And to show that a value is excluded, we use a parentheses. From that point, the graph goes up forever, towards positive infinity.
So let's just do a quick recap of the big ideas. A relation is just a set of xy pairs showing a connection. The domain is your list of all possible inputs, the x's. The range is your list of all possible outputs, the y's. We can show these connections in 4 different ways, and we have special tools like interval notation to help us describe relations that have an infinite number of points. We started this whole thing by saying that math is a language, and now you're equipped with some of its most fundamental grammar. So I'll leave you with this question. Now that you can read the language of relations, what other hidden connections out there in the world could you start to describe? What relationships can you see now that might have been invisible to you before?